Welcome to Escape Velocity Space News. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. This week's show run has changed faster than we could write the episode, with an ever-changing array of bad news pouring out of the aerospace industry. It is safe to say the theme for this show could have very easily been Space is Hard. But in the final rewrite of the show, we made a choice to run brief on the bad spacecraft news and run long on the science. Here is what we're not discussing in detail. The SpaceX Falcon 9 and Falcon Heavy launch vehicles are grounded after a second-stage launch mishap that led to the loss of an entire batch of Starlinks. Also potentially grounded is the much-anticipated Europa Clipper, which was built with transistors not manufactured to spec and may not be able to survive the high-radiation environment at Jupiter without a major rebuild. NASA is working the problem, and when we know if the mission is delayed or will fly as is, we'll bring you detailed coverage. Finally, I'm not going to go into detail on how mega constellations are harming the ozone layer or how the increased cadence of rocket launches is adding to global warming. Instead of all of that, we're going to focus on new discoveries that bring joy. From black holes to Jupiter's great red spot, we're bringing you the good news from science right here, right now on EVSN, a product of CosmoQuest, and supported by our patrons at patreon.com/CosmoQuestX. It turns out Jupiter likes to have giant red spots, but it doesn't always have the same giant red spot. New research led by Agustin Sanchez Lavaja and appearing in Geophysical Research Letters looks through nearly 350 years of telescopic data on Jupiter and finds clear evidence of Jupiter not having a giant spot from roughly 1713 to 1831. Prior to 1713, numerous astronomers, including discoverer J.D. Cassini, documented what they called Jupiter's permanent spot. Their careful sketches allowed modern researchers to document how the spot observed in the 1600s and 1700s both decreased in size prior to disappearing and also appeared to drift in its location in ways markedly different from what today's Great Red Spot appears to do. It has long been wondered if this was just a fluke of observations, but they pored over historic observing logs and found no evidence for the Great Red Spot, despite repeated observations by greats such as Herschel and Messier. While sketches of Jupiter noted banding like we see today, as well as other storms, the complete absence of the red spot ultimately points to a lack of Great Red Spot during that period. The Great Red Spot we see today was first observed in 1831 and has been continuously observed ever since. Early sketches and photos taken since the late 1800s all show that the Great Red Spot started out much larger and much more stretched out. Over time, it has gotten rounder, smaller, and has drifted slightly northward. This paper raises the interesting possibility that one day we might wake up to no more Great Red Spot. On one hand, that would make for some super cool science. But I, for one, hope this long-sustained vortex will outlive me and allow astrophotographers to continue to practice their craft on its spinning goodness. I don't think there is an astronomer who doesn't love a pretty high-resolution image of, well, pretty much anything in space. Give me a crisp, clear galaxy or nebula, or even a quiet frost field on another planet, and I will happily stare at the pretty picture. But science. The coolest science sometimes comes from the gnarliest looking images. Back in May and October of 2023, the Juno spacecraft flew near Jupiter's volcanic moon Io and pointed its infrared camera at Io to see what it could see. And what it saw was lava lakes that appear hottest around the edges. The data isn't pretty, but the story it tells is neat. It's now thought that as much as 3% of Io's surface is covered in molten lava lakes. Many have what could be solid shells over their central regions and are ringed by still molten lava. Contained within high-walled caldera, these lava lakes are geologically similar to the Loco Opelli lava lake at the peak of Kilauea volcano. And it's due to the very behavior that gives lava lamps their name. As lava wells up, it cools in the center and then sinks down. According to Juno co-investigator Alessandra Murra, quote, "We now have an idea of what is the most frequent type of volcanism on Io. Enormous lakes of lava where magma goes up and down. The lava crust is forced to break against the walls of the lake, forming the typical lava rings seen in Hawaiian lava lakes. The walls are likely hundreds of meters high, which explains why magma is generally not observed spilling out." End quote. The images used in this initial release from NASA are just the first of what should be increasingly detailed information from Juno's additional Io flybys in December 2023 and February 2024. When discoveries from those datasets are published, we'll bring them to you right here on EVSN. Here on Earth, we often talk about planetary analogs. These are areas where the landscape here on our planet is geologically similar to other worlds. There are regions in the Atacama Desert, for instance, that are very similar to Mars. Today, as researchers look back at Cassini data of Saturn's moon Titan, researchers can imagine Earth analog landscapes where methane-ethane seas erode away their shores in much the same way water waves here erode shorelines on Earth. In a new paper in Science Advances, researchers led by Rose Palermo use simulations to demonstrate that the shorelines on Titan are consistent with wave-driven erosion. As team member Taylor Perrone points out, quote, "If we could stand at the edge of one of Titan's seas, we might see waves of liquid methane and ethane lapping on the shore and crashing on the coasts during storms. And they would be capable of eroding the material that the coast is made of." End quote. This research isn't definitive. Other forces could be at play shaping Titan's beaches. We won't know until we are able to go back. Luckily, the Dragonfly mission looks to launch in 2028 and arrive at Titan in 2034 with robotic rotorcraft that will explore Titan's surface. After the break, we're going to leave planetary science behind and take a look at black holes. Stay tuned. My entire life, researchers have been asking, are there black holes in the hearts of dwarf galaxies and globular clusters? We know they lurk in the centers of large galaxies, and their sizes are proportional to the sizes and motions of the spheroids of stars they occupy. It has long been hoped that the relationship would extend down to smaller spheres of stars, but we just haven't been able to find any evidence until now. As the story goes so far, astronomers have found binary star systems where only one star is visible and its motions indicate a second mass so small and dense that only a black hole can explain what we see. These stellar mass black holes range from 5 to 150 solar masses in size. On the other side of the size scale, the motions of stars and gas in the cores of galaxies indicate the presence of supermassive black holes with masses larger than 100,000 solar masses. It's been assumed that black holes between 150 and 100,000 solar masses should exist, but it's easy to hide when you don't emit or reflect light, and black holes don't emit or reflect light. Our best guess for their hiding place has been inside dwarf galaxies or globular clusters, but studies to date haven't been good enough to definitively rule in or rule out their existence. But over time, the availability of new data can allow new discoveries. For the past 20 years, the Hubble Space Telescope has been periodically and for myriad purposes taking images of the Omega Centauri globular cluster. This is a unique globular cluster for both its size and composition. It is 10 times more massive than a typical globular cluster, and its stars appear to have experienced multiple generations of star formation, with supernovae blasting gas out of the system in ways that have led to really weird ratios of different kinds of atoms in the different generations of stars. Put another way, Omega Cent is just plain weird, so people keep finding reasons to look at it with Hubble. Over 20 years, Hubble has taken more than 500 images, and a team led by Maximilian Hebrelli recently reviewed these images in detail, looking for the telltale signs of stellar motions that a significant mass would cause. Looking at just the innermost 3% of the cluster, they were able to find 7 stars with just the kinds of motions that are expected. Oh, and an arc second is the angular size of a piece of hair held at arm's length. Essentially, your little finger at arm's length is about 1 degree of arc across. And there are 60 minutes in a degree and 60 arc seconds in a minute, or 60 strands of hair in 1/60th of your finger size at arm's length. These stars are moving across the sky at 2.41 milli-arc seconds a year. This is a ridiculously small amount, but with 20 years of data and 500 images to study, even these tiny movements can be seen. These on-the-sky motions work out to physical velocities greater than 62 kilometers per second. Under normal circumstances, based on what we see, these velocities would be greater than the cluster's expected escape velocity, and these stars would be unbound from the system. But they're not unbound. This indicates there must be a hidden mass that is gravitationally holding on to the stars and causing their motions. According to calculations by Hebrel's team, a black hole with a mass around 8,200 solar masses would invisibly provide the needed gravitational pull. And this is right in the middle of that intermediate mass black hole range. An undergraduate working with this project, Matthew Whitaker, explains this discovery in a way that truly delights me. He says, quote, "There are black holes a little heavier than our sun that are like ants or spiders. They're hard to spot, but kind of everywhere throughout the universe. Then you've got supermassive black holes that are like Godzilla in the centers of galaxies, tearing things up, and we can see them easily. Then these intermediate mass black holes are kind of on the level of Bigfoot. Spotting them is like finding the first evidence for Bigfoot. People are going to freak out." End quote. I'm not sure the joyous celebration of astronomers over this discovery is quite on par with what I'd expect if Bigfoot were actually discovered. But I think this was, as collaborator Anel Selth put it, quote, "a once-in-a-career kind of finding," end quote. I can now only hope that year by year, the data we've gathered of other smaller systems eventually allows us to identify other intermediate mass black holes. This work appears in a new paper in Nature. Understanding the observed population of black holes is one of the more weird tasks astronomers find themselves faced with. The LIGO and Virgo gravitational wave detectors are capable of measuring signals from the merger of all sizes of stellar mass black holes. In general, in our universe, smaller things greatly outnumber larger things. But in the gravitational wave data, there are significantly more detections of black holes with masses between 20 and 100 solar masses than lower mass systems between 5 and 20 solar masses. In another new paper in Nature, researchers led by Presmek Mrose consider the weirdness of this mass distribution, and they suggest perhaps we're seeing the mergers of a population of primordial black holes that formed in the early universe that was predicted by Yakov Zildovich. If this is the case, these 100 solar mass black holes could explain at least some of the dark matter known to exist in our universe. Essentially, these black holes that are invisibly haunting the outskirts of galaxies and spaces between star systems could be part of the universe's missing mass. They can't be more than 3% of dark matter, or we'd see other well-predicted effects, but 3% of dark matter is 3% we couldn't explain before. These particular black holes are cool because they're predicted to have formed in a way unlike other stellar mass black holes. Early in the universe, mass wasn't evenly distributed, and while slightly more dense regions formed galaxies or even stars, some particularly chunky regions could have formed these black holes. And these black holes might have even formed before those stars and galaxies. With each new set of observations, it feels like we understand our universe a bit more. And our universe is just that much weirder. After the break, we'll be back with this week's Tales from the Launchpad. Stay tuned. And now for a rundown of all that launched, or at least tried to. On June 22nd, China launched the Space Environment Monitoring Satellite from the Shenzhen spaceport. Let's watch the launch. SVOM is a collaboration between the Chinese National Space Agency and the French Space Agency. It has an X-ray telescope and will be used to rapidly identify gamma-ray bursts from the explosions of massive stars for follow-up by ground-based instruments. It weighs less than 1 metric ton, and the mirror itself, the most complicated part of an X-ray telescope, is a mere 1 kilogram. On June 25th, SpaceX launched the GOES-U spacecraft into geostationary orbit on a Falcon Heavy for NASA and NOAA. Let's watch the launch.
5, 4, 3, 2, 1, ignition, engine full power, and liftoff. Go SpaceX, go Falcon Heavy, go NOAA, go NASA, and go you.
Vehicle is pitching downrange. Engine chamber pressure is nominal.
GOES-U is the fourth and final satellite in the GOES-R series. When it reaches its operational orbit, it will be named GOES-19 and take up the west station along with GOES-18, currently in the east position. It will be operational until at least 2036. And yes, these are ridiculously named satellites. On June 28th, SpaceX launched NROL-186 from Slick 4E at the Vandenberg Space Force Base in California. On board were more satellites for NRO's proliferated architecture of satellites using a custom Starlink bus for an intelligence mission. The first launch of this type of satellite was NROL-146 last month. Let's watch the launch.
5, 4, 3, 2, 1, ignition. And liftoff. Falcon 9, go SpaceX, go NROL-186. Vehicle is pitching downrange. Stage 1 chamber pressure nominal.
As is typical for NRO launches, no coverage of the second stage and payload was allowed, so the brief webcast focused on the first stage's successful landing on the Of Course I Still Love You drone ship a few hundred miles downrange. On June 29th, China launched the ChinaSat 3A satellite into orbit on a Long March 7A rocket. Not much is known about the satellite. It was given the name ChinaSat 3A and a description that was of a broadcast satellite for TV and satellite internet, but it's suspected to actually have a military purpose. The launch took place from China's New Island spaceport on Hainan, where the stages fall into the ocean. Also on June 29, JAXA launched the ALOS-4 satellite on the third launch of their new H-3 rocket. This is its first operational mission after a launch failure on the first flight and a dummy payload on the second. ALOS-4 is a synthetic aperture radar satellite using an instrument developed by Mitsubishi, who also make military and civilian aircraft, tanks, warships, bulk carriers, cars, spacecraft, and rice cookers. It's for land observation. It's an improved version of the instrument flown on ALS-2. ALOS-4 also includes an AIS receiver for automatically identifying and tracking ships at sea. On July 3rd, Firefly Aerospace launched their Noise of Summer mission from the former Slick 2W at Vandenberg Space Force Base in California. Let's watch the launch.
5, 4, 3, 2.
On board were the 8 CubeSats of NASA's Alana 43 mission: CatSat, CubeSat, MESat, R5S4, R5S2-2, Serenity, SOC-I, and TechEdu 11 for a variety of NASA and university teams. All payloads but CatSat were successfully deployed into a stable orbit. It's likely that CatSat's provided deployment mechanism failed to function. All other payloads had Firefly-provided deployment mechanisms. Alpha's second stage performed a relight after separating most of the satellites to validate changes to the stage following the relight failure of previous missions that left its payload in a useless orbit. The test was successful. There were also 4 launches of Starlink satellites, of which one failed rather remarkably, causing the Falcon series of rockets to earn itself a FAA investigation. We keep track of orbital launches by launch site, also called spaceport. According to RocketLaunch.live, so far this year, the USA has had 84 launches, China 31, Russia 8, India and Iran 2 each, French Guiana and North Korea 1 each. Of these 133 launches, there have been 5 failures, reminding us space is hard. Before we go, I just want to take a moment to share something beautiful. Out of the blue, I received an email from an artist and infographic designer, Martin Varjek. And I have to admit, few random emails have been quite so pleasing. He just wanted to let me know that he'd produced an infographic highlighting vast diversities of worlds that have been discovered since 1992. From pulsar orbiting planets to gas giants to Earth-like worlds, he has included a little bit of everything in his poster of over 1,100 known worlds, in which each world is depicted through a combination of known data, things like temperature, mass, and radius, and inferred geology and atmospheric possibilities. In a separate infographic, he looks at almost 900 icy and rocky exoplanets and charts them out by temperature. This is just stunning science, and digital versions can be explored entirely for free. This is your reminder. Information is beautiful. And that's it for now. Good night, everyone. And remember to go out and look up. Oh, and please give this video a like and subscribe so the algorithm tells you and the world when new science is ready to be learned. And if you have things you want to see in future episodes, drop it in the comments.